Welcome back to our final lesson in our unit on reasoning and proof as we look at some of the reasoning that is specific to geometry, as we look to justify and prove some of the theorems that are out there in geometry. So we'll get through some of the basics, kind of review some of the things we've talked about with points, lines, and planes, which is where we'll start off first here. Here are some postulates. They're numbered here. They aren't doesn't mean that's the specific number that we need to refer to. It's just a number that certain textbooks refer to. But here are some of the things we talk about with points, lines, and postulate or planes rather. First of all, through any 2 points, there's exactly one line. Okay, and as we look at a line, we know that in the reverse of that, a line contains at least 2 points. Next, when lines intersect, when they cross, their intersection is exactly 1 point. We refer to that point as the point of intersection. Next, through any 3 non-collinear points, there exists exactly 1 plane. The key there is they're non-collinear. And then also, a plane contains at least 3 non-collinear points. Next, if 2 points line a plane, the line containing them lies in the plane. So if the points are in the plane, the lines have to be in the plane. And finally, if 2 planes intersect, the intersection is a line. Okay? So lines intersect, they intersect in a point. Planes intersect on a line. Okay? Here are some diagrams that illustrate those postulates. First postulate that we looked at, if 2 lines intersect, then they intersect at 1 point. If 2 planes intersect, notice these planes are crossing, they intersect at a line. You can kind of visualize that 2 walls. And where 2 walls meet, there's a line. Okay? Let's take a look and see if we can identify some other postulates here. Notice this plane, plane P. Notice there's a line M on that plane. So that means that the points on that line are in this plane, plane P as well. Notice we have points B, A, and C. Those are 3 non-collinear points. So those 3 points are also on the plane, or in the plane. Plane BAC or plane P, we could refer to it. Notice we've illustrated that where 2 lines intersect, there's a point of intersection, point A. Also, where 2 planes intersect, their line of intersection is line M here. Okay, so those are some of the postulates. A postulate is something that doesn't need to be proven. It's just a rule that's accepted. It kind of goes along with our definitions of points, lines, and planes that we'll refer to throughout the year. Let's take a look at a diagram once again and how we can interpret that. We've talked about this a little bit before, what we can assume and what we can't. When we interpret a diagram, we can assume information about size or measure only if it is marked. Okay, so we can assume that all these points, since they're lying in the plane, are coplanar. There are no points up here in a dashed line showing that it's another dimension. We can't assume that G, F, and E are collinear. The reason is there's no line connecting them. We can say that A, H, J, and D are collinear because those are connected by a line. Okay. We can say that angle AHB and angle BHD are a linear pair. That would be this angle here, AHB and BHD. Those form a linear pair since they share a common ray. They're right next to each other. Okay. The next thing that we can take a look at is that AHF, that's this angle here, and BHD, those are vertical angles since they share a common vertex. They have opposite rays. We talked about how AH, J, and D are collinear because they are connected with a line. And line AD and line BF intersect at H since they are labeled there. I already mentioned we can't assume that G, F, and E excuse me, are collinear. because they're not connected by a line. Line BF and CE intersect. Looks like they probably will eventually down here if we were to continue the line, but since our diagram doesn't explicitly say that or show that it intersects, we can't assume that it does. It just might be a poorly drawn diagram. And also we can't say that they do not intersect. We don't know if the lines are parallel. We cannot say that angle BHA and angle CJA are congruent either, even though they might look like they are, unless the markings are there to show that we cannot say it. The other thing we can't say is if lines are perpendicular, so like AD and line BF. Though it appears that they might be perpendicular, what we would need in there is a marking to show that they are perpendicular. That box in the corner would indicate if they are. Now, if we want to sketch a diagram according to the postulates that we've just looked at, we need to sketch the information that we're given. So it says sketch a diagram showing line TV intersecting segment PQ at point W. So that segment TW is congruent to segment WV. So I need at least 2 points on a line. It says they need to be labeled TV. And it intersects segment PQ at point W. So the point of intersection is W. I know that that has to be a point because two lines intersect at a point. And now TW is congruent to WV. Okay, so to indicate that that length is the same, even though it appears that it might not be, remember I need to put the tick marks in here to show that those two segments, segment TW is congruent to segment WV. So since we can't assume anything, we need to include all the measurements to show that those segments are congruent. Now let's take a look at some statements, see if we can interpret. I'd like you to try answering these checking these 5 statements and see if we can assume the information given. Pause it and come back when you are ready. A, B, and F are collinear. Can we assume that? They're connected by a line, so yes. We know they're collinear. E, B, and D are collinear. Well, they're not connected by a line, so we cannot assume that they are collinear. Segment AB is perpendicular to plane S. That's the red one here. I see the marking in the corner here that indicates a right angle, so that would make it perpendicular. Segment CD is at perpendicular to plane T. That's the blue one. There's no marking here, so I cannot assume it, whether it is or not. And line AF intersects line BC at point B. Two lines intersect at a point. That point is B. So yes, I can assume that. Okay, so unless the diagram tells it, we cannot assume. So now this comic illustrates a property that we'll be taking a look at. It's known as the transitive property. The transitive property kind of goes like this. So paper beat rock, scissors beat paper. Therefore, since scissors beat paper and paper beat rock, scissors should beat the rock. Okay, so that's the transitive property. Even though it doesn't apply here with rock, paper, scissors, it is a property that we will be taking a look at. So first property is the reflexive property. So the reflexive property, even though it might seem like an odd thing that we're using, the reflexive property is used so we can state that something is equal to itself, kind of like reflection shows yourself in the mirror. We can state the reflexive property when we're proving something. So if we're using that when we're talking about algebra for any real number A, we would say A equals A. Okay, it just shows that it's the same thing. And we're talking about segment length AB, well, we'd say that AB is equal to AB. Okay, so we use that when we're just trying to show that a segment might be in two different segments, part of two different segments. We can show that that little portion is the same. And for any angle measure, angle A, we say that angle A is equal to angle A. Okay, seems kind of odd that we'd have to say that, but it's a way that we can show that something is in two different, if it's part of two different segments or two different angles, we can show that that part's the same. Symmetric property, this one we can use when we're showing that, similarly, if something is equal to, if A is equal to B, like in algebra, if one variable is equal to another, we can flip that around and it doesn't change anything. Kind of like symmetry shows that it's the same on both sides. Same with a segment. If we have two segments A, B, and CD and they're equal, well, if AB equals CD, then, well, CD would have to be equal to AB. Okay? And for angles A and B, if measure of A equals measure of B, then, well, measure of B, we could say, be equal to measure of angle A. Okay, so that's the symmetric property. Think symmetry, it's the same on both sides. And the transitive property is the one that we're talking about with the rock, paper, scissors comic. So notice for different numbers, if A equals B and B equals C, well, then we know that A and C are the same. It's kind of like that law of syllogism that we had talked about earlier. Same with segment lengths. If we have three different segments, and if the first one's equal to the second one, that second one's equal to the third one, we know the first one has to be equal to the third one. We know that they are all the same length. Okay? So AB would be equal to EF. Okay? And then for an angle measure, if the first angle measure is equal to the second, second's equal to the third, we would know that, well, they are all the same. We could say the first one is equal to the third one. Measure of A is equal to measure of angle C. So that's the transitive property. That's kind of like that law of syllogism that we talked about. So let's take a look at our initial stages of proof. Okay, so if we have this figure here and we're trying to show that angle EBA is congruent to angle DBC. Okay, well, the first thing we know is that angle 1 and angle 3 are congruent because they're marked so. Okay, we can say that that is those are given to us. Okay, it's given in the diagram that those two angles are the same. Well, what else do we know? Well, if we're trying to prove that EBA, which is made up of angles 2 and 3, is equal to DBC, which is made up of angles 1 and 2, well, they both have angle 2 in them. So let's use that information. So first of all, let's show that angle EBA is equal to measure of angle 3 plus measure of angle 2. It's that angle addition postulate that we talked about. Those two smaller angles, they equal the bigger angle. Same way we can say that EBA is now equal to measure of 1 plus 2 because, well, 1 is the same as 3, so we can just substitute 1 in for 3. It's the same measure. That's the substitution property of equality. Next, we can say that, well, 1 plus 2 equal angle DBC because that's the angle addition postulate once again. Okay, we're trying to show that these two bigger angles are equal, so we need to show that they're made up of the same smaller angle measurements. So now, since we've shown that angle EBA is equal to 1 and 2, and DBC is equal to 1 plus 2, well, they're both equal to measure of 1 plus 2, so they have to be the same by the transitive property. This one's equal, first one's equal to second, second's equal to third, so they have to be the same. So that is the beginning stages of proof that we'll start to take a look at as we go throughout the year. We're going to be proving different theorems in different ways. We'll talk about paragraph proofs. We'll talk about flow proofs. This is just the beginning stages of how we justify something. Just like you did in algebra when you justified solving an equation, we need to justify different theorems that we come across and prove that they are really indeed true. So we took a look at different properties that we can help as we begin to prove things. We took a look at the reflexive and symmetric and transitive properties. We'll use those in our proofs. And we also took a look at some of the different postulates that dealt with lines, points, and planes. You'll do some practice with that in your practice problems and start to develop the proof as we go through the year. All right, we'll see you next time.